So we're looking at the fourth worksheet for acid and bases in grade 12 chemistry, acid-base concepts number 4. Have this in front of you if you haven't done it, and pause the video as necessary to try the questions yourself, okay? If you don't just watch and don't just copy what I'm doing if you can. It's better for your understanding if you do it yourself. So question number 1, pause the video and see if you can figure that out. We have 4 solutions here. We're asked to circle the one that's most acidic, and we want to cross out the one that's most basic. And what makes this irritating is that the information given is different in each of the beakers. We have a pH, we have a hydronium, we have a POH, and we have a hydroxide. It's hard to compare them when they're all different. So a good thing to do would be to make them all refer to the same thing. So for example, most people find looking at pH to be easiest. So for all 4 beakers, let's figure out what the pH is. In the first one, we're given the pH, so there's nothing to do there. The second one, the hydronium is 0.010. That's 10 to the minus 2. The pH is the negative log of hydronium, so you could grab a calculator if you want, the negative log of 0.010, or maybe you could do that in your head because 0.01 is 10 to the negative 2. This pH is going to be 2. Okay, so now you can see right away, I can tell now that because it has a lower pH than the first beaker, the second beaker is more acidic. The first beaker is more basic. Okay? The one with the higher pH is more basic. The one with the lower pH is more acidic. The third beaker gives us the POH, 3.25. At 25 degrees Celsius, the pH plus the POH gives you 14. So if we want to find the pH, we'll just subtract 14 minus this number. So 14 minus 3.25. This pH is very high. It's 10.75. So now we can tell right away this so far is the beaker that's most basic. The last beaker gives us the hydroxide. So why don't we first figure out the POH. We'll take the negative log of the hydroxide's concentration. Then we'll subtract that from 14 to figure out the pH. So first, the negative logarithm of 2 times 10 to the minus 5. The POH is 4.70, and then subtract that from 14. This guy's pH is 9.30. Okay, so be sure you're able to do those things on your own calculator. Now that I see the pH values, the question becomes very simple. The one that's most acidic would have the lowest pH value. So let's circle the one with the lowest pH value. The one that's most basic or alkaline, that's another word for basic, would have the highest pH value, and we're told to cross that one out. So this guy here has the highest pH value. Question 2, pause and see if you can fill in the conjugate acids and bases. So if you're given an acid and you want its conjugate base, you just remember that acids donate their hydrogen ions. So take the HPO4 2-, give away the hydrogen ion, and what you're left with is PO4, the phosphate ion. And because this guy started off as 2-, you lose a hydrogen, which is positive. Now it's going to be 3-. The charge goes down when you lose a hydrogen. If you're given a base and you want the conjugate acid, then you simply remember bases accept hydrogens, right? So HPO4 2-, when it accepts a hydrogen, it'll become H2PO4. And because it accepted a hydrogen, the H2PO4 is going to be minus. All right, so we notice right there that the HPO4 2- in the first part was an acid, but in the second one it was a base. That means this thing was amphoteric, right? Amphoteric meant that in some situations HPO4 2- can be an acid. It has hydrogens to give away. while in other situations it could be a base. Because it was negatively charged, it can accept hydrogen ions. So any species that is negatively charged and has hydrogen ions as well, like this, will be amphoteric. It can be an acid or a base. HOCl, we're told here it's an acid. If it loses its hydrogen ion, you'll have OCl minus, and that's its conjugate base. Sulfite, SO3 2 minus, is a base. If it accepts a hydrogen ion, you'll have HSO3, and it's accepting a positive, so the charge goes up by 1, and now it's minus. Question 3 is a titration question, which is really just a stoichiometry question. We're told that we're standardizing a solution of sodium hydroxide. Sodium hydroxide is a base, a strong base. It has a metal, sodium, attached to hydroxide, and that's the formula for a strong base. We're told we're standardizing a solution of sodium hydroxide, which means we're going to find its concentration exactly, right? To standardize a solution is to determine what its concentration is. We're going to use a monoprotic primary standard acid. This is exactly the acid we used in our lab. Monoprotic, so it's an acid with just one hydrogen. So why don't we simply call it HA in our balanced equations? It's a primary standard, which is a fancy way of saying this acid is pure, right? It's pure. And we're told it's a molar mass, 204.2. So we want to complete the results table here. We look and we're given the initial and final level of sodium hydroxide. That would have been in a burette, right? When you do a titration, you use a piece of glassware called a burette. You filled it with the sodium hydroxide solution, and initially the level was 0.95 milliliters. Then you add the sodium hydroxide from the burette to a flask underneath. And that flask contains acid. In this case, we used 0.426 grams of the KHP, the monoprotic acid. As the base reacts with the acid, they're neutralized. And we stop adding the base when the acid that was in the flask is exactly neutralized. Okay, and it turns out here we stopped at 27.13 milliliters, the level of NaOH at the end. So to do the question, we're going to want to have a balanced equation, right? Because there's stoichiometry involved in titration problems. The acid was monoprotic, just HA, and the base here is sodium hydroxide. So this looks like a double replacement reaction. We want the H's from the acid to be equal in number to the OH's in the base. Here there's one of each, so we're good to go. If they weren't equal, we'd put a number in front of one of them, a coefficient, to make the H's and OH's equal. In this case, the H and the OH combine and give me water. And then we're left with some type of salt, and the salt here, we'll just call it sodium A. We're using HA as the formula for the acid because KHP is actually not a chemical formula. The K, yes, is potassium. The H, yes, is hydrogen, but the P there just stands for phthalate. Phthalate is not an element on the periodic table. Phthalate is a complicated organic molecule. So KHP is actually not a chemical formula. So we're using HA to represent the acid. So we can see that the acid and base react in a 1-to-1 ratio. So the first thing we want is the moles of acid used. If you know what you're doing, pause the video and see if you can calculate how many moles of KHP the student used. To find moles, we'll just take the mass and divide by the molar mass if you want to use a formula. Or we can use a unit multiplier. We can take 0.426 grams of the acid, and we can convert the grams to moles using the molar mass, 204.2. That was given up in the question. So 0.426 divided by 204.2. We're going to keep 3 significant digits in our answer. The moles of KHP, I'll just put my answer in the table. 0.00209 moles of acid. Now, how many moles of base were used? We know the moles of acid, and we're asked for moles of base. That's the stoichiometry question. That's where we use the balanced equation. So we'll take our 0.00209 moles of acid, and with 1 unit multiplier, we'll convert the moles of acid to moles of base. And from the balanced equation, the ratios here, there's 1 mole of base reacts with 1 mole of acid, so we can see it's actually going to be the same number, 0.00209. If they were reacting in a 2-to-1 ratio or a 3-to-1 ratio, then we would know when we set up that multiplier if we should multiply by 2 or divide by 2, multiply by 3 or divide by 3, etc. The next thing is how many milliliters of sodium hydroxide were used. While looking up at the burette, we know the initial and we know the final level from the burette, so we just subtract those two numbers. 27.13 milliliters minus 0.95 milliliters, the student used 26.18 milliliters of base. Convert that to liters by just dividing by 1,000, and you'll have 0.02618 liters. And finally, we want the concentration of the sodium hydroxide. Well, you remember concentration is moles divided by volume, where the volume is in liters. So we're just going to take the moles of base, 0.00209, and divide by the volume of base, 0.02618. And we get, with 3 significant digits in our answer, 0.0798 moles per liter. And now we know the concentration of the base has been standardized. Question 4, pause and see if you can just write the balanced equation for the complete neutralization of the sulfuric acid H2SO3 with potassium hydroxide KOH. So this acid is diprotic, and it's going to react with our strong base. Again, I know that's a strong base because it starts with a metal, potassium, the left side of the periodic table, bonded to hydroxide. That's a strong base. Before I write any products, I'm going to balance the H's and OH's. There's 2 H's in my acid and only 1 OH in the base, and I want those to be equal. So I'm going to put a 2 in front of the KOH. That gives me 2 hydroxides, which will neutralize the 2 H's in the acid. I'm neutralizing them like that because we were told it's a complete neutralization, so both of those hydrogens in the acid require hydroxides to be neutralized. The H's and OH's create water, but because we had 2 H's and 2 OH's, it gives us 2 waters. And then there's a salt produced. The salt would be potassium sulfite, and because there's a 2 in front of the potassium, the formula must be K2SO3. There's our balanced equation. Pause the video. Can you calculate the pH and the ionization percentage for 0.5 molar acetic acid? So acetic acid is a monoprotic acid. The hydrogen at the end is the acidic hydrogen, the one that gets donated. It'll react with water. It's dissolved in water and reacts with water. It donates a hydrogen to the water, creating hydronium, and then what's left behind with the acid is the acetate ion. Okay? You might be able to hear my cat whining there. So we're going to set up an ice table. The acetic acid is 0.5 molar. The water is a liquid, we'll ignore it. The hydronium in water is so small, 1 times 10 to the minus 7 molarity, that we'll ignore it and just say the hydronium is 0. And the acetate is 0 initially. Acetic acid is a weak acid. We look up its Ka value in a data booklet or in a Ka chart if you have one. The Ka for acetic acid is 1.8 times 10 to the minus 5. And that means it's not going to ionize completely, so we'll just say it loses X. The ratios are 1 to 1, so these guys will gain X. So we have 0.5 minus X, and these guys are X's. Now we'll set up the Ka expression. That's the hydronium concentration times the acetate concentration divided by the acetic acid concentration. 1.8 times 10 to the minus 5, the Ka value is X squared over 0.5 minus X. If you have a solver on a graphing calculator, go ahead and solve that. For those of us without the solver, we'll use the approximation method. So we'll notice that since the Ka is small, you have to say this in your answer, we're going to assume that the X is much less than that 0.50. So look at the denominator of our expression. It said 0.5 minus X. If we assume that X is much smaller than 0.5, then when you subtract X from 0.5, your answer should be very close to 0.5. So we get a simpler equation. 1.8 times 10 to the minus 5 is approximately X squared over 0.5. We just ignore the minus X, and we just say 0.5. Grab a calculator and solve that. Our first answer will be the first approximation to the original equation. So 0.5 multiplied by the Ka equals, and then square root the answer you get. The first answer is 0.0030 molarity. Now we'll get a second approximation by taking the first approximation and putting it back into the original equation where we ignored the X. So in other words, we're going to put it in the denominator and say 0.5 minus 0.003. And then we'll solve for the X in the numerator. So on our calculator, 0.5, I'm starting in the denominator, 0.5 minus 0.003, the first approximation, equals, take this answer and multiply by the Ka value out front, equals, this is equal to X squared, the numerator. So we'll now square root the answer, and we get the same thing. We get, when rounded off, 0.00299, which becomes 0.0030 molarity. Because my answer stopped changing, we're done. That's the concentration of the hydronium. Look at your ice table. That's the hydronium's concentration. So the pH is the negative log of hydronium. So we'll say negative log of H3O, which is negative log 0.0030. Because the concentration has two significant digits, we'll keep 2 decimal places in our pH answer. 2.52 is the pH of that solution. We were also asked to find the percent ionization. Okay, so we look back at the acid in the ice table. Its initial concentration was 0.5. The amount that ionized, the amount that it lost, was X. So to figure out the percent ionization, we simply take the amount that ionized, the X value, and divide that by the starting concentration and times by 100. So it's a weak acid. It does not completely ionize, but we can see here it ends up being 0.60% ionized, less than 1%. It's 0.6%. All right. Question 6. We have a weak acid whose formula here is just generic. We're just calling it HA, right? There's no element on the periodic table with a symbol of A, so this is just a generic formula for a monoprotic acid, has 1 hydrogen. We're told it's 2.5% ionized, and we want to know the Ka for the acid. Well, let's write a balanced equation. The acid HA reacts with water, producing hydronium and A minus. Fill in the initial line of your ice table. The acid is 0.010 molarity. The water is a liquid, so we'll ignore it. The initial hydronium is so small in water that we'll say it's 0, and there is no A minus. All right, now we're trying to find the Ka value. So I don't want to start filling this in with x's because I don't know the Ka. So filling it in with x's won't be very helpful. But we know that the acid is 2.5% ionized. In other words, if we go to the side, we can take 2.5%, so over 100, of our starting concentration, and this is going to tell me how much of the acid ionized. So 2.5 over 100, 2.5% of the starting amount, 0.01. We now know that 2.5 times 10 to the minus 4 molarity is what ionized. So what do I do with that? Well, in my ice table, this is how much ionized, so this is how much we lose, 2.5 times 10 to the minus 4. Now you can fill in your table and go ahead and calculate Ka. So these guys will gain 2.5 times 10 to the minus 4. It's a 1-to-1 ratio. And when you take 0.01 minus that small number, now we have 0.009. I'm going to be a little bit loose with my sig figs here, and I'll round off at the end. So there's my concentration for HA. The Ka value, we'll write the expression. It's the hydronium times the conjugate base over the acid, HA, and that's going to be 2.5 times 10 to the minus 4 squared, multiplied by itself, divided by 0.00975. So 2.5 times 10 to the minus 4 squared divided by 0.00975. This was a weak acid, and its Ka should be small, and we get 6.4 times 10 to the minus 6 as the Ka value for the acid. Notice if we wanted to find the pH, we could. The pH is the negative log of the hydronium, and we know the concentration of the hydronium, so finding the pH would be pretty simple too. Some questions are like this, but instead of telling us the percent ionized, they tell us the pH. They'll say a 0.01 molar solution of a weak acid has a pH of some value. And then they'll say, what's the Ka of the acid? So you'd set it up like we did here, but then instead of using a percent ionization on the side, you'd use your pH. They told you the pH, so you would do 10 to the power of negative pH, which would then give you your hydronium, right? If you know the pH, you can calculate your hydronium as 10 to the negative pH. When you know your hydronium, you could put that into the ice table and then fill in the table and calculate the Ka value. So that's another permutation of this kind of question. And finally, we want to rank these three solutions in order of decreasing strength as electrolytes. So electrolytes, these are solutions where there are lots of ions present, and therefore they conduct electricity very well. So which of these three substances will produce the most ions when dissolved in water? That would be the strongest electrolyte. Which one produces the least ions? And that would be the weakest electrolyte. Well, pause and see if you can figure that out. So the first substance here, sodium sulfate, what is that? Well, it's just a salt, right? Sodium sulfate. It's a salt, and in grade 11 chemistry, you know that when you put a salt like sodium sulfate in water, it's a salt that has alkali metal, sodium at the beginning. It's highly soluble and it just dissolves. And as it dissolves, it turns into sodium ions and sulfate ions. So this sodium sulfate, notice the concentrations are all the same, it's going to produce lots of ions. If you have 0.1 molar sodium sulfate, you'll have 0.2 molar sodium, twice the concentration because there's a 2 in front of the sodium, and you'll have 0.1 molar sulfate. So this guy's going to actually end up having 0.3 molarity ions. Now the sulfuric acid is the second thing there, H2SO4. We notice that it's a diprotic acid, and it has two steps, right? Step one, it's going to produce hydrogen ions, or hydronium if you like, and HSO4 minus, and it does that completely because it's a strong acid. So it's going to produce a lot of ions. But then in a second step, the HSO4 minus goes on to ionize a second time, but that step is actually very weak, right? It's not very weak, but it's a weak ionization. So it does not ionize completely in a second step. So the first step was strong. It's going to produce 1 mole of hydronium and 1 mole of HSO4, 1-to-1 ratio. But then the second step is weak. So of those two, because the first one produces 3 moles of ions for every 1 mole of sodium sulfate, the second one produces only 2 moles of ions for every 1 mole of the acid, and then a little bit more in a second step. So right now I'm thinking the first guy is a better electrolyte because it's producing more ions. And then H3PO4, well, you might be tempted to say that it's got 3 hydrogens, it's going to be the most ions. But although, yes, it's going to have 3 steps in its ionization, remember that it's a weak acid even in the first step. So it really doesn't produce much ions in the first step. And the second and third steps have really small Ka values compared to the first. So we just ignore those usually. So phosphoric acid, even though it looks like it will have lots of ions, it actually doesn't produce much ions because all 3 steps of its ionization are weak. So the weakest electrolyte was the weak acid. The strongest electrolyte here turned out to be the salt because it completely breaks apart into ions, and there's 3 ions for every 1 particle of salt. The sulfuric acid is the second best electrolyte there because it does ionize completely in a first step and only partly in a second step. All right, so I hope that makes some sense. So there's worksheet number 4, a good review of a lot of ideas in the acid-base chemistry unit.